Hey there, math fans. Making another video on common arithmetic errors I have seen in my calculus courses. I just made a video about distributing an arithmetic and how often I've seen that on tests, and I'm hoping to dispel that. This is a big one. This is at least as big as the distribution one, maybe bigger, in terms of the number of errors I've seen that have to do with fractions. And I'm just going to talk about a particular type of error I've seen with fractions. And it kind of boils down to this. So here are 5 examples that all come from my final exam in Math 125, which is a Calculus 2 course from fall 2024. It's a strong course. I had 480 students. These are students that got into the University of Washington, have always been good at math. And they take this final exam, and they're having to do big problems. And in the middle of it, they did this bit of arithmetic / algebra, whatever you want to call it. And these are all things I noted that I saw. And I saw a lot of these. So I want you to think for a second, which of those are valid? And I find even just looking at those, students are unsure. The truth is, only one of those is valid. So I saw a whole bunch of errors. By a whole bunch, I don't know, 20% of students made an error of this type somewhere on the exam, 25%. But that's a large number considering the sample I'm talking about is students that were the top of their school in high school. So this is a big problem that's holding people back. And students go, oh, I just made a silly algebra mistake. But that's a big mistake. So let's go through and first talk about checking your work. This is there's one idea to sort of resolve, in my opinion. If you don't remember whatever your fractions rules are, and I don't remember, students come in and they're like, sometimes you flip, sometimes you don't flip. I don't know when you flip. And I know a lot of people use those successfully, but I don't think about that. I just use one very simple idea for all fraction problems. So I'm going to give you that in a second. And that's what I teach to students rather than have to teach them a bunch of different rules. Okay, so the first thing, and this applies to all arithmetic algebra things you're doing, is it's usually very easy to check. And the way you check is you plug in x equals 0 and you plug in x equals 1. And maybe you plug in x equals 2. Because in order for you to say that two things are always equal, they have to be equal for all values. Eventually you get to a point where you don't even need to plug in a number. You can just see it's wrong. But if you're not there yet and you do a step and you don't know if it's right, just plug in 0 to both sides. It's super easy. If I plug in 0 to this side, I get 0 plus 1, which is 1. If I plug in 0 to this side, I get 0. Are those the same? No. So those are not equal. In fact, it pained me to write that. But I saw that a lot. Out of 480 exams, I probably saw 12 students make that mistake. To me, that's a lot. Okay, what about this one? Try to plug in 0 to both sides. If you plug in 0 to the left side, you get 1. If you plug in 0 to the right, you get error. They're not the same. Again, probably saw half a dozen students make that mistake. This is a prevalent mistake. It doesn't just happen here. It happens all the time. This one. Now, this is part of one that I'm going to talk about in a second. But this is a student that saw this and they're like, okay, I remember this rule about flipping. So they flipped. Let's check. If you plug in a 0 here, you get a half. You plug a 0 here, you get a half. So maybe they are the same. If you plug in a 1 here, you get a 1. If you plug in a 1 here, you get a 1/2 over 2. Now what is that if you plug that into your calculator? Now there's a little bit of not real ambiguity here, but sort of ambiguity, which is by the fact that this is a really big bar, this is implying that these two things are together. And lack of anything else, and this is part of what I'm going to talk about in a second, part of the reason there's this big confusion, you can't flip this. But that was a good example where I plugged in 0 and they were the same, but I plugged in 1 and they were not the same. Because if I plug in 1, it's going to be a 4th. Some people have to plug in their calculator. So if you're still unsure, plug into your calculator, but hopefully you don't have to get there. This one, when I plug in 0, they both give me an error. So that's all right. When I plug in a 1, I get 6 over 1, and then I get 5 plus 1 is 6. Oh, when I plug in a 2, I get 7 over 2. 5 over 2 plus 1 is 2. 7 over 2. Okay, this one I'm unsure about. So this one, no. This one might be right. But you can see how I don't trust my algebra. I'm running in every time I do something, I kind of look forward and backwards. Maybe I haven't plugged in a number. Are these reasonable? This needs to be your thinking. In math, we think in terms of proofs and counterexamples every step of the way. If you're unsure, just think of a counterexample. This is another example of a student just remembering some rule about flipping. And this is what I'm worried about. This is what I've seen. And students think they're right because they're just like, well, I flipped it. And I was told something about flipping. But here again, you can see if you plug in 0 on the left, you get 3/8. If you plug in 0 on the right, you get an error. So first observation is we can quickly check our work. But the second observation is let's not make those errors. Okay, so now I have a very short lesson in the following idea. And I think when people see this, they've never really thought about it. So I'm going to write down 6. I'm going to write down divided by 3, and I'm going to write down divided by 2. Order matters in division. So usually what I tell students to do is do 6 divided by 3 and write 2 over 2 and tell me what that is. 1. If you were with me now, that's what I'd have you do. Then I would say, okay, I want you to do it a different way. I want you to tell me what this is first. Instead of telling me what this is first, which is what I did, I want to know what this is first. Well, that's 1.5. Okay, now I want you to take 6 and divide by 1.5. It's 4. Whoa. So usually when I show that to people for the first time, they're like, what? Those are different? And that kind of highlights this misunderstanding, which is that, yeah, it matters. Order of division matters. And so if you just have a random idea about whenever you see a fraction you flip, you're not going to get the right answer. Only in one of these situations does flipping work to give you the right answer. Try that and see. So if you did 6 times 2 over 3, what do you get? Well, it's a separate question. Most students do 12 over 3, which is correct, but also wrong, because you should do 6 divided by 3 is 2 and then say it's 4. That only does it for this one. It doesn't do it for the other one. So this idea of flipping your fraction is going to get it wrong in the first case and going to get it right in the second case. So sometimes you'll get lucky, sometimes you won't. Okay, so I don't ever use this idea of flipping. Okay. Instead, if somebody gives me a fraction, I ask them where the big bar is. So where is the big bar? So in this case, the big bar is here. And a lot of times when we're doing calculus, even in books, they just highlight one bar over the other, and we sort of miss this. They don't put these parentheses here. I think it comes from an age of where it would be kind of a pain to do that. But what I like to think of instead is just multiply the top and bottom, the numerator and denominator, by the same number. And that is something, if you've worked with fractions through your grade school days, you've done a lot. Back when someone was teaching you how to add fractions and you had to do 1/3 plus 1/2, you got a common denominator. How did you do that? You multiplied top and bottom by 2, and you multiplied top and bottom by 3. Why was that legal? That was legal because you're just multiplying by 1. This gave you 2/6. That's a different story of talking about this, and then you added them together. This idea is the only idea I use when working with fractions. I never think about flipping. It never made sense to me to have to memorize when to flip, when I knew that I could just multiply top and bottom of a fraction by the same number, and it doesn't change anything, but it just changes the look. Okay, so if we want to change the look of a fraction, what do? We find the big bar, which is this here, and I multiply top and bottom of that by something that will get rid of one of my fractions. And that something would be 3, because when I multiply this by 3, those 3's will cancel. And this will become 6 on top 6 on bottom, and it's 1. So typically multiplying the top and bottom by something answers your question right away. So here, I would say this is the big bar, and I would multiply top and bottom by 2. Why 2? Because that gets rid of my other fraction. And this would be 12 over 3, which is 4. I do everything like that. Find your big bar, multiply top and bottom. Okay, I mean, this first example is more an example of adding fractions, but even here the principle is at play, because I would be taking the 1 and multiplying it times 2 over 2 to get a common denominator, and then I would write x plus 2 over 2. Now that's not better, so there's no real good way to simplify this, but I just wanted to illustrate this principle of this. That's the only tool I use, because I know I'm multiplying by 1. I know that's legal always. Okay, so here what can we do? Well, it's this issue of people thinking they can break things up. It doesn't work that way. There's really nothing I can do here to simplify this. I could multiply, I mean, if you wanted to be goofy, you could multiply top and bottom by a half. What would that do? That would make this a 1. It would make this a 1. It would make this x over 2. Did that serve any purpose? Not really. But I know it's legal. Okay. What about this one? So this one I would have said, I want to multiply top and bottom of the big bar by 2. Notice I'm not even thinking about flipping at all. And now the top will become 1, and the bottom will just become 2x plus 1. And if you don't know if you can distribute, then watch my previous video, but here we can distribute. So what I like is I like having rules that I understand and have universality. I find students like to have something that they like, a routine they can use, but as soon as you hit a situation where this random routine of flipping doesn't perfectly fit and you don't understand why, then you're in trouble. Okay, in this case, it's true because of a common denominator thing. We're really distributing. This is an example of distributing. Watch my previous video about that. Because the denominator is not changing. We're actually just doing 5 over x plus x over x. That's legal. That is the same. Okay, this last one is just crazy. My video got briefly interrupted, so I'm going to continue here, and I unfortunately erased a couple things, but I think we'll be all right. So we're down to this last one, and what happened here, this is an example, I think, of a student that knew something about flipping fractions, and they didn't know what to do, so they just flipped random things. And so this is a really good example of what I'm talking about, which is identify where the big bar is. That's pretty clear here. And I would multiply top and bottom. Now you could multiply top and bottom by 2 to get rid of that 2. You can multiply top and bottom by 8 to get rid of the 8. But you might realize, oh, 8 will also get rid of the 2. What I like about this is you could stop right here, and anybody could look at this and be like, okay, this is legal because I'm multiplying by 1. And then you get 3 over, that's going to be 4x plus 8. It's just so nice and clean that you can do it that way. Okay, so that's the main thing I wanted to say. You know, this applies even if there's variables, like if you have 3 over x minus 2, same thing. The big bar is typically very clear. You multiply top and bottom by x, you get 3 over x squared minus 2x. So that's the idea. Just this general idea of multiplying the top and bottom. There's other stuff I can say about fractions that comes up when you're solving equations, but I'll leave that for a different discussion. Here we're just trying to simplify expressions. What I mean by that is you're given an expression, meaning there's no equal sign anywhere, and we're trying to simplify. In those situations, you can always multiply the top and bottom by the same thing to change the look of it, which means you never have to have a fraction within a fraction. You can always get rid of it by using this one technique. All right, hope that makes sense. Hope that helps you, and hopefully you won't make these errors when you take your calculus courses.